So let's talk about something that sounds like it's pulled straight out of a science fiction movie. Imagine a liquid that can flow forever without any friction. A liquid that conducts heat perfectly, and maybe weirdest of all, a liquid that can actually climb walls and just ignore gravity. Well, this isn't fiction. This is superfluid helium. Here's how we're going to break it down. First, we're going to witness its impossible gravity-defying behavior. Then we'll dive into the quantum secret that actually makes it all possible. We'll explore its strange dual personality, see how it's become this critical super tool for science, and finally take a look at what's next for these incredible quantum fluids. All right, let's start with the single most mind-bending thing this liquid can do. It's something that seems to just break one of the most fundamental laws of nature. It's a simple question, right? And the answer is just bizarre. I mean, in our everyday world, liquids spill down. They settle at the bottom of a glass. Gravity always wins. But what if it didn't? This is what's known as the rolling film. A cup of superfluid helium won't just sit there. An impossibly thin film of the stuff will spontaneously start to climb the inner walls, flow right over the lip, and drip down the outside until the whole container is empty. It's like gravity is just a mild suggestion. So how in the world is this even possible? Well, the answer isn't in the physics we see every day. To get it, we have to go deep into the strange world of quantum mechanics at temperatures colder than anything you'd ever find in nature. And when I say cold, I mean unbelievably cold. At just 2.17 Kelvin, that's only about 2 degrees above absolute zero, something amazing happens. Helium hits this very precise temperature called the lambda point. And fun fact, it gets that name because if you graph its specific heat, the chart looks exactly like the Greek letter lambda. This is the exact moment it transforms into a totally new state of matter. Now, this isn't some brand new discovery. It was actually first spotted way back in 1938 by Piotr Kapitsa. And in what has to be a fantastic coincidence of science, it was independently confirmed that very same year by John Allen and Don Misner. What they stumbled upon became a cornerstone of modern physics. And this new state is called superfluidity. To get a handle on that, just think about viscosity, a fluid's internal friction. Honey is super thick, so it has high viscosity. Water is thin, so it has low viscosity. Well, a superfluid has zero viscosity. None. It's a perfect frictionless fluid that, if you set it in motion, could just keep flowing forever. And this transformation is just dramatic. Look at the difference here. Normal liquid helium has viscosity. It boils like crazy. But the second you cross that lambda point, it becomes perfectly still. Its viscosity vanishes, its ability to conduct heat goes through the roof, and most importantly, it stops being a classical substance and becomes a quantum one. The atoms stop behaving like a chaotic crowd and start moving in perfect unison. Imagine that crowd suddenly marching in perfect synchronized step. That's what's happening. They all act like one single massive quantum object. So to explain this wild behavior, scientists came up with a really clever model. I mean, how can something act like a normal liquid and this new quantum thing at the same time? They imagine it as two separate fluids that are mixed together, occupying the same exact space. You've got a normal part that still has some viscosity and acts like you'd expect, but mixed in with it is the superfluid component, the part with zero viscosity that's responsible for all the wild quantum stuff like climbing up walls. And this balance, this mix, it totally changes with the temperature. As you can see, right after it crosses the lambda point, the liquid is still mostly the normal component. But as you get colder and colder, closer to absolute zero, the superfluid part starts to take over, until pretty soon the entire liquid is in this perfect frictionless quantum state. Okay, so a wall-climbing, frictionless liquid is an amazing party trick, for sure. But why does it actually matter? Well, it turns out these bizarre properties make superfluid helium one of the most powerful tools in all of modern science. These unique properties are what make it so incredibly useful. Zero viscosity means it can flow without any resistance. Its thermal conductivity is thousands of times better than copper, so it can wick heat away perfectly. It can slip through tiny pores that would stop any other liquid cold. And it even forms these things called quantized vortices, tiny perfect whirlpools that are a direct sign of its quantum nature. These aren't just weird quirks, they are legit engineering superpowers. And here's where we see those superpowers in action. In places like the Large Hadron Collider, you've got these massive superconducting magnets generating insane amounts of heat. Superfluid helium is pretty much the only thing that can cool them down effectively, pulling that heat away with perfect efficiency so those incredible experiments can keep running. It's also absolutely vital for exploring the cosmos. To get those crystal clear images of faraway galaxies, the sensitive detectors on space telescopes have to be kept unimaginably cold and stable. Superfluid helium provides that perfect, ultra-cooled environment, letting us see deeper into the universe than we ever could before. And it's paving the way for our quantum future. The processors in quantum computers are unbelievably fragile. They have to be isolated from even the tiniest amount of heat or vibration. Superfluid helium creates the perfect, silent and frigid environment that we need to build and operate the powerful computers of tomorrow. But the story doesn't end here, not by a long shot. The discovery of superfluidity basically cracked open a whole new field of research, and scientists are still exploring its deepest mysteries today. Right now, researchers are trying to understand things like quantum turbulence, the strange, almost orderly chaos that happens in a frictionless fluid. They're even on the hunt for something called a supersolid. Think about that for a second. A material that's a rigid solid but could still have atoms flowing right through it without any friction. Ultimately, what superfluid helium showed us is that when you push matter to its absolute limits, the rules that we think we know just break down, and they reveal a much deeper, much stranger reality underneath. It really makes you wonder, doesn't it? What other impossible states of matter are just waiting for us to find them, down there at the edge of absolute zero?